I love it when these are, attended by people from all around the world. That's absolutely fantastic.
That is
So while we're waiting for a few people to show up, I'm just going to do a couple of quick announcements, and then I'll turn it over to John Musgrave. So with that said, let's see here. So everybody, this is Alex Gosorek. I'm the Audio Engineering Society's Vice President for the Western United States and Canada. I'd like to say hello, everybody, to this evening's presentation from your local section of the Los Angeles area. I just want to do quick announcements. Finally, we have some live events that you can attend in person that are starting to occur. We actually have the very first one occurring literally in a few weeks, which is in Europe, the European Convention, which you can attend in person and then online. Then we also have some other upcoming events. Some of them are online and then other things in person as the year goes on. AES Immersive Academy in Music and Streaming, that is in the end of April. We have the Spring Convention, which I just mentioned, which is in May, early May. We have a conference in Ecuador, and then other AES academies, including the AES Academy at NAM. Yes, NAM is back. It's going to be back in Anaheim, but this time it's going to be in June, and we will be there with some of our presentations. But most importantly, the AES convention in the fall. And that's going to be on October 19th and 20th. That will be in New York City. And then the following weekend, if I'm not mistaken, will be online. So there'll be a sort of a hybrid approach. And that's basically how the conventions will be for some time, that hybrid approach. All that information is on the AES's website, aes.org. Go to the events tab, find out the information there, register for what you'd like to go and attend, and we will see you there. With that said, I am now going to turn this over to John Musgrave. And I'm going to say, I'm turning off my camera for now. I'll still be listening in, but hello again from Las Vegas, and I'll be attending this next time from Phoenix. So on to you, John.
Thank you very much. Ladies and gentlemen, I want to welcome you to the Los Angeles section of the AES, our monthly meeting. And tonight we are looking at dynamic equalizers, in particular plugins, and we're going to look at the difference between graphic and parametric, and kind of focus on the parametric side of life. And we have Duane Wise with us. He is a developer. He's been developing for a good 20 years. Isn't that correct, Duane? Not that long?
Yeah, yes, it is.
And then we have Nathaniel Kunkel, super user. He's been using the plugin pretty hardcore, and he's here to talk about it in different ways to make the plugin his friend. And so we have the Q&A tab that is different than the chat tab. And so if you have questions, put them on the Q&A tab, because we follow that, and the chat is more for everyone in the audience and saying hello and that kind of stuff. And Duane, would you like to take it away?
Certainly. Thank you, John.
You bet.
Okay, so my name is Duane Wise, and I'm the founder and president of Wholegrain Digital Systems LLC. And probably the best thing I can do right now is cut my camera and start screen sharing. I'm going to go through a few briefing slides and then a very short demo, and then hand things over to Nathaniel. So, screen share. All right, here we are. Let me move this over here. Okay. So, I will cite the date of 1970, probably quite at least multiple times. So we just passed the 50th anniversary of the parametric EQ as we know it. But my contention is that we as audio engineers work at one station within what I call the audio chain, and there are two terminals of this chain. The very receiving end of this chain is where the intended audience is, and at or near there we are looking at loudspeakers, or we are looking at the human hearing system, and how both of those entities are conceived of is that they're conceived of multiple subbands, be it the speakers in a larger cabinet, or the bark bands within our psychoacoustic model of hearing. But this is a system that has concatenated and independent subbands, and we take these subbands and we put them next to each other with virtually no overlap. And this is a EQ system where we start from 0 and we just add in all of these subbands until we have covered the entire band of interest. And this is basically how graphic EQ works. And within those subbands, we can then we can then adjust levels within those subbands to actually equalize things to where we actually want them to be once, once the signal reaches the intended destination. And be it just the bass, mid-range, and treble dials, or a 10-band graphic EQ, or a 30-band, they tend to be employed more in playback systems. But at the very other end of this audio chain is where we actually capture the acoustic sources making these acoustic signals. So we are actually looking at instruments, we're looking at rooms, and we're looking at microphones. And let's take the example of a violin. The bow creates acoustic energy in a string, and that string hits the bridge, and that bridge is what is called an impedance mismatch. And what that means is that some of the acoustic energy will actually pass through into the bridge, but most of it will be reflected back into the string. But critically, some of that will actually pass through, and within that bridge has its own independent set of resonant nodes and resonant nulls. Once it hits the bottom of that bridge, though, that is the interface to the very top plate of that violin, which is another impedance mismatch. Most of the energy will be reflected back into the bridge, but some of it will transmit to that top plate, and that top plate has an entirely different independent set of its own resonant nodes and resonant nulls, and then it hits the side plate, which is another impedance mismatch interface, and then it meets the bottom plate, which is yet another another impedance mismatch interface. But at that bottom plate, it then tends to start to get the air in motion by it, by the resonance of the bottom plate. So now we're looking at the acoustics of the interior of the violin until the signal reaches the holes, and then it becomes an issue of the acoustics of the room. Every transition from one of these little acoustical subsystems has its own independent resonant nodes and resonant nulls. But since it transmits through these impedance mismatches, it is actually composing with the other subsystems via what we call a cascade, which is a multiplicative operation rather than an additive operation. George Massenburg presented his original paper outlining the concept of the parametric EQ in 1970, so just over 50 years ago.
1972. It was presented in 72.
72?
Yep.
Okay, I thought it was 1970. So it's 50 years now. 50 years of PEQ. Hooray, right?
Yeah, 42nd AES convention in 72.
Cool. Okay. So a parametric EQ, as it is presented to us, usually only has a few bands. And the reason for that, I contend, is that you can assign one parametric band to deal with one acoustic issue that you are encountering with this source performance track. So, our acoustic systems are basically good, but you might have this, this violin or this room just has a dead spot or a live spot. And after that presentation, the 1970s, the parametric EQ was widely adopted in recording studios. And I am sufficiently old that I remember the Marantz parametric EQ that you could buy for your home stereo system. And that was one of the very few parametric EQs that companies tried to market towards the home user. It never really caught on. And I contend that that makes a lot of sense because it is not really an optimal fit for the destination end of the audio chain. It's a very good fit for this end. So I'm going to move on to the next slide. But for a lot of equalization and dynamic EQ applications that you can find as plugins these days, most of them actually base their architecture on the graphic EQ or the crossover network. And from a computer science standpoint, that actually makes a lot of sense because employing a graphic EQ setup is ideal for employing parallel processing, because your subbands can be processed independently. And you can also use what is known as the short-time Fourier transform, so that you can do your processing in the spectral domain rather than the time domain, and that can actually get you fairly significant computational savings. One side effect of using the short-time Fourier transform, though, is that you have to do your frequency domain processing on entire blocks of samples at one time. So it's block by block by block. And that leads to, when you do your level measurements for dynamic reaction, you are doing the level measurement on an entire block of samples rather than going sample by sample by sample. Similarly, you react to those level changes block by block by block. And this is the reason why, if you have a dynamic EQ system, some of them sound a little bit sluggish. You really can't get a very fast reaction from it. When you base a software-based processor on a parametric EQ, on the other hand, parametric bands must be implemented in series, and within that band is a recursive filter. Both of those things force you to do your processing in the time domain rather than the frequency domain. So you are processing things sample by sample by sample inherently, so that we can carry on that sample by sample processing and give you real-time level measurements and real-time reaction, so that if you base a multi-band dynamic processor on a parametric EQ, you can legitimately support very fast attack times and release times. But that doesn't necessarily mean that that you must perform your processing much as an analog system must. So one thing that that our company's software does is that we actually borrow a principle from the short-time Fourier transform to actually make those level measurements much more flat and robust over time, such that you get much less harmonic distortion. And I will show you just for very quickly a slide of how things are set up. We have a basic dynamics processor here, which takes a sidechain signal, does a level measurement, puts it against a what we call a dynamics curve, which gives you a real-time gain signal. And if this were a broadband a dynamics processor, it would then feed something much like a VCA or a broadband amplifier. Well, we've swapped out that VCA and we've replaced it with a parametric filter. And the other thing we've done is that we take the sidechain signal and we put it through its related, what I call a pre-filter. So if this is a peak dip, this is its corresponding band pass. If this is a low shelf, this is the corresponding low pass. It will share the cutoff frequency of the related parametric filters. So this will isolate the band that we're processing on in the sidechain so that we get band filtered input that we send to our level system. And our input level will then be reflected on where we plot the dynamics curve. The input level is on the x-axis, the desired output level is on the y-axis, and the difference between those two is the effective boost cut. And this dashed line is neutral gain. So the parametric part of this band will have a static boost cut to it, and that's reflected as the solid line. But any additional boost cut we then apply dynamically will be reflected in the edge of the shaded area offset from our static boost cut. So if we must really tear on here. So I'm going to give you a very short demonstration, and here we go. This is a stereo track of an acoustic guitar recording. I'm going to play you about 15 seconds of it right now. So that sounds pretty good, except for one little thing to my ear. On the strum of the guitar, the pick strike has, to my ears, an extra component in it that sounds a little bit like a breath mint being dropped onto a kitchen counter. So it sounds more like a click than it does an actual pick. So I'm going to use this blue band to do a four-step technique that I go through exhaustively in my product seminars. And as a matter of fact, I'm going to drop into the chat window right now, since I think most of you are here who are going to be here. I've put into the chat window such things as when is the next seminar, and what you can do to get yourself a trial code, and a few more URLs. We are going to be at NAMM, 3rd through the 5th of June, room 14924. And following NAMM, I should be in town for roughly a week. So if you would like a studio visit, please get in touch. I would be happy to do that. But all right, so now we have a quick 4-step procedure for exerting dynamic control on bands. First thing I'm going to do is I'm going to alt-click this band in-out thing. This usually brings the band in and out. But I'm going to alt-click to actually put this into a special mode called sidechain search, and that does two things. First thing it does is that we'll actually be listening to the output of the pre-filtered sidechain. So we'll actually be searching for that band where that click noise is actually coming from. And I have a feeling that it's going to be fairly high Q. So I actually want to start with a Q that's higher than what I'm going to actually use. So we're just listening for the very crown of that band. And I'm going to start things now. And now we look at the center frequency of the peak dip. And I think our click type noise starts roughly around here and goes through up till about here. So let's listen for a center. And I'm thinking the center is somewhere around here. Okay, so now let's lower that Q value. We'll actually hear everything start to rise, but we want that click sound to stop raising in volume when I lower the Q. Everything's getting louder, but that click level is pretty much covered with this Q here. So that's step one, is finding that band. Step two is finding the worst case level that we get here. So I'm going to do a quick stop and we'll go back to the beginning now. While I do this measuring of our worst case level, I'm going to activate the compression part and I'm going to put it into a special mode called rotation point, and I cover all of this exhaustively in my product seminars, but we kind of have to rip through it now. And I think that we're not actually going to get a higher level than 21 within this band. So I'm going to place that rotation point along the x-axis, along input level at -21. So we take it out of sidechain search now, do a regular click on any of these blue buttons. Step 3 is we offset this rotation point so that we've taken care of that click. This is not enough. This is probably too much. I'm thinking we can take care of it somewhere around here. Okay? But now we hear that there is some notch filtering here. But we've taken care of that click noise. So I'm going to go back to the beginning now. So we have a gain at threshold, extra parameter. We actually give this some compression ratio now, such that once we get to this worst case level, which is where that strum is, we are taking care of the signal there, but we raise the ratio. We have this extra parameter called gain at threshold, where this compression line puts a virtual threshold once this relative gain hits our line of neutral gain, this dashed line where the output level is the same as the input level. So now let's take the compression in and out. We hear that click back, and we pretty much taken care of it here. So let's play with the attack and release times now. Note that strum is a very short duration. So I pre-adjusted the attack and release times to be their very fastest values. So let's play with them. Let's set the attack time to something we would more normally use, something between 12 milliseconds and 15. So let's listen to it now. There really isn't much of a difference here. So with this very slow attack time, we're actually missing that strum stroke. So pretty much by necessity, we have to have an extremely fast attack time to actually cover that. Now, let's set the release time to something we would more normally use, something between 10 and 15, or 100 and 150. Now that notch filtering has come back in. So because of the short duration of that strum, the release time really should be extremely short too. So this is a four-step method. We actually find the center frequency and we adjust the EQ. Measure, we get that worst case. Then step 3 is control, where we offset that to actually cover our worst case. And then the last step is balance, where we then give it positive ratio such that outside of our worst case, it is processing something more normally. So, this has been a very quick demonstration of our product, and I should probably move things right along now and hand things back to John. Thank you very much. I'll stop screen sharing and put the camera back on.
Perfect. So in that demonstration right there, you were showing that not only, when we think of EQ, we think of it like, pulling out sound, that's missing, or if we have too much of something that's making it boomy or flubbery or, whatever the adjective is. But utilizing the dynamic EQ, we're able to actually go in and surgically pull out clicks, noises, little artifacts that are that we don't want in the performance. Correct? Whoops, you're muted.
Oh. I should be back now. Oh, all right.
Back.
So, yeah. Most people use it as you can actually use it as just a straight parametric EQ. I put into the chat window a URL for Mix with the Masters, and that is a pointer to a Mix with the Masters video series with Alan Meyerson, and how he uses it is that he can use it as a straight parametric EQ, but when he's doing these incredibly large-scale mixes, there is a point where he kind of wants to use it as a meta EQ, so that in extreme cases he can get all of these tracks to fit together into one, very limited audio space. And I think that Nathaniel can probably vouch for that as well.
Right. Yeah, and that's what I was thinking. And to get things to fit, and if you have something, maybe a performance where a part of it that's getting a little bit excited and a harshness comes out, you can grab that harshness in that moment that it gets, because of the increase in level and everything like that, and then pull it down.
Right. That actual pick noise may be that the pick was metallic rather than plastic. It also may have been a plastic pick that had a crack in it, and that crack just rubs and has its own click element. But probably most likely was that the microphone just had a very sensitive high frequency region, and that pick stroke was just making it pop. and you just want to reduce that pop.
Right. And then, so what is the latency? It's pretty quick, right? Because it's all it's pretty much real time, where like a block, if you're doing 512 samples for your block or something, then that's, that's stretching out into a little bit longer.
Yes. Let's see. We have two flavors of our dynamic parametric EQ, trio and quartet. Trio is the 3-band. Its latency at 48K is 2 milliseconds. And quartet is our 4-band version that also supports multi-channel stems. And its latency is I think 3 1/3 milliseconds or 3.5 at 48K.
Right. And can you, is there the availability of changing one of the bands to be a shelving function?
Sure, yes. If you want me to go back to screen sharing, but I think we should get over the bulk of things, and if there's anything specialized someone would like to take a look at, we can do that afterwards.
All right, that sounds good to me. So, Nathaniel, what is your favorite application of this of dynamic filtering? You have do you have a, you use it, so do you have a go-to moment where it's like, in every mix, like some people will throw something across a bus and it's their everything? What's your everything moment for the for dynamic EQ?
Well, everything. I mean, like it's one of the reasons why I don't do these too much for Duane, is it sounds too much like I sound too much like a shill, right? Like because, for me, once you start really analyzing sound, all sound, you guys have been focusing on acoustically generated sound, but all sound, whether it comes from a synthesizer or a tom-tom or a piano or a voice, or I mean anything, whether it's music concrete, whatever it is, it's not dynamic with totally timbral uniformity, right? Like there isn't an instrument in the world that comes up and down totally timbrally, flat, like, and which can be used to many, psychoacoustic benefits, right? Because like one of my favorite like tricks, like John Leventhal used to do this, where he would take like a drum head that wasn't even on a drum, and he would just tap it with his fingers, and he'd put a microphone on it, and your brain understands what that component of dynamic textures means. It means that you're unbelievably close to it. Oh, it's only when you're really close to something does that combination of textures arrive at your ear, right? So it feels like it's just enormous. And so when you start to really hear sound broken down into the components of it that have different dynamic identities, as it were, right? And you guys are picking one that's very simple, which is, here's this click on a guitar. One that's minorly more complicated are the arbitrary resonances within a singer. Like there won't be 50 or 100 of them, but there might be 3, right? Where you have to, you'll find like that there are little notes or places where a singer will just whistle, like, you'll get all this energy in a really disproportionate amount to the amount of level you're getting out of everything else. And so when you start hearing things that way, you can start approaching the way you I was going to say fix, but that's really not the right word. The way you alter the sounds that you're listening to do so in a less heavy-handed way, right? Everybody uses compressors all the time, but if the problem that you're having is at 150 hertz and it's only an octave wide, and you put that into an 1176, you know, we understand the idea of high pass filter or anything so that all the low frequency doesn't make a broadband limiter go, but that happens all the way up the frequency range, right? And the only reason that we don't get into trouble is the thing that Duane pointed out earlier, which is most compressors are too slow to really address stuff that up that high in a way that's too damaging. But I think so for me, I use it everywhere because I end up getting shit louder and I do less work, right? You know, if I can dynamically take care of this thing that's happening at 150 and that's 2 or 3 dB or 4 dB, and I can take care of this thing that's happening at 3K or 6K, dynamically kind of tight with a lot of gain reduction, then all of a sudden everything else is everything else comes up to 6 dB, right? I get apparent level everywhere else because those other very sort of relatively small problem areas aren't sort of poking through and becoming part of the general level averaging of what that instrument is.
Right, and that's my impression. It's a really good fit device because, you know, if you have things that are kind of popping out, if you're putting something broadband on it to dynamically control it and bring it back in, then you're kind of stepping on everything at once. And with the dynamics on a band, and you're able to just go in and surgically get what you want, then it's kind of like a fitting tool. And then again, like you were saying with the vocals, if someone, when they're pushing, a certain aspect comes out a little bit more than feels good or sounds right or fits within the track, then you can kind of step on that and bring it back without stepping on the rest of the character of the performance.
Yes, exactly. And so, and the thing that makes quartet, you know, or this whole algorithm, kind of everything we've been talking about so far are kind of general approaches, right? There are other dynamic parametric equalizers out there. The thing that makes this different, and again, something that Duane touched on, is the sheer speed with which it works, right? So like if I've got a vocal that I really, really need to stand up, I'm right in the middle of, yeah. Just give me one moment. If I have a vocal that I really, really need to stand up, sometimes I'll end up taking out 9, 10, 15 dB of sort of problematic S ranges, right? When I can really find out where that spot is. I'll end up doing some really, really drastic equalization, because then ultimately I don't have to do very much else to the vocal. I can put 5 or 10 dB of RMS general level compression on it, and I can turn that thing all the way up.
Oh, right.
Right? You know, like
gentle broadband.
Exactly, because those little spiky things that have become problematic for me in a dynamic way, I've really been able to harness.
Right. Now I have a question for you, Duane. Is there like a key or a side chain where you can then use that to modulate the program that's being EQ'd with a different track to create, you know, modulations and different things? So if you're working swells and that type of stuff.
Yes. The 3-band system, trio Dyne PEQ, is a single channel insert, and it does support the separate sidechain in Pro Tools. So yes, and Quartet in its current version also supports the sidechain, but for the mono version of that plugin only. In the next version, we will probably support the monophonic sidechain in the multi-channel processor as well. That has been a request, and I think we can do it. So.
And have you in the design aspects, have you had trouble with losing speed of the device fitting more into it and having to take up more processor time? Has that been a issue for you?
Not really. The main issue of processing time for this particular processor is that if I may go back to screen sharing, is that we a Dyne PEQ processor will do its level measurement on the total RMS level, and what we mean by that is that not only will it calculate the RMS of the kinetic energy of the signal, but it will also separately calculate the RMS of the potential energy of the signal, and that potential energy is 90 degrees out of phase. But when you add those separate energy signals, you'll actually get something that for an input sine wave is something that's quite flat. So this was what I referred to in that previous slide, in that we can actually borrow a principle from the short-time Fourier transform. Well, that principle is the measurement of total RMS energy, rather than what you usually get with an analog-based level measurement, which is the rectified wave with a level follower with a very long release time, and give you a very flat modulating signal that lessens the chance of harmonic distortion.
So, Nathaniel.
So how that manifests is that you can as Duane was showing, you can find where your problem frequencies are. You can figure out what the Q is of that issue, and then you really can dial in the timing characteristics of that band for what the problem is, not what the band's capable of doing from a timing standpoint. Like up until quartet, if you wanted to do some sort of really, really fast release time, you came up against distortion artifact, right? Like it was a question of, can I make this run fast enough versus how much distortion am I going to get out of the band? That is a non-issue when you're working with Trio or with the Dyne PEQ. And so because, and by the way, we've been talking about it in terms of high frequency stuff, right? Because that's obvious, right? S's and things like that. Being able to get out of compression incredibly quickly is critical to being able to do enough gain reduction, right? The amount of gain reduction you do is primarily dictated by how fast of a release you can tolerate on the filter. So being able to, the decisions you make about what the filter timing characteristics are be delineated by what the audio is that you're analyzing, not by what the capabilities of the filter are, is a totally different way of approaching it. It's much more, it's much more scalpel. You have to, Unfortunately, Duane falls into the same problem that Massenburg fell into with the 8900, right? Just people see the word release hysteresis and they just go running the other direction with their hair on fire. And so, it's a tool that you have to really understand what it is you're trying to do. Like that scenario that Duane proffered at the very beginning, there's so many reasons why it's such a good scenario, right? The very first thing that's important to know, to realize about it, is the way he organized searching for that, which is he listened to the audio and he identified a problem, right? And so so much of the way people approach audio is, well, put that plug in on it and see what it does, or put that plug in on it and see what it does. Whereas if you approach a sound like, here's the sound, here's what I hear, here's what I need to fix. And what I need to fix is a dynamic issue, whether it's a broadband dynamic issue, whether it's a tight Q dynamic issue. And by the way, low frequency shelves and high frequency shelves are also brilliant on this box. Like, talk about being able to just sort proximity effect out on a microphone. Like a low frequency shelf just solves that problem for you. But when you hear exactly what the problem is, this is the perfect tool for it. But really understanding what the parameters do, even that's sort of valueless if you're approaching this particular tool without an understanding of what you're trying to make it do when you instantiate it.
Right. So I have an interesting question. So do you ever find yourself using this plugin just kind of as a scope? Maybe you're hearing something and a dynamic EQ isn't what you're thinking of utilizing in the way of actual processing, but you're curious to what in the hell am I hearing? And then you break out the dynamic PEQ and do some searching with the window there and find out what you have and what the bandwidth is, and then how to attack it with something else?
Well, much like The Simpsons, George did it first. So ISO peak is something that I've been using for years, and it was first implemented in the MDW EQ, and so now, of course, I do it in the Dyne PEQ, but I use that function all the time. Right. Whether I'm going to be setting up a dynamic or a static EQ filter section.
Right. Find out, where the problem is, and then and it's more intelligent and quicker to pull it out with the result you want.
But I mean, I'm to the point now where I couldn't mix without Dyne PEQ. That's not it is absolutely a go-to for me.
It's a friend.
John?
Yes.
John, you were mentioning processing time. So this level measurement, since we have to do two separate RMS calculations and then add them together, if it is quartet working on a multi-channel stem, that has to be done for each channel. And since our dynamics rail is implemented for each band, this has to be implemented for each band on each channel. So bands multiplied by channels means that this rather expensive operation can be the thing that slows it down the most, and that is why there is a control on the quartet plugin, which I can bring up here. Actually, it's not here because it's mono and rats. Well, the multi-channel quartet will have a little control that says RMS calculation. You have a choice of fast or slow, and fast or slow just basically says how much computer time would you like to devote to calculating the total RMS of your multi-channel input signal.
And then one of them just gives you a higher resolution number than the fast.
It is a difference of actually being sufficiently anal retentive to calculate all of the RMSs for all of the bands and all of the channels, and then summing them into one thing. Or the fast version is summing all of the sidechain signals into a single a single sidechain channel, and then doing the measurement on that. So with that single sidechain input, you run the potential of having some phase cancellations and whatnot, but you can speed things up.
I see what you're saying. That makes sense. Excellent. Is there any do you have anything to add, Nathaniel? You just disappeared, but and if anyone has any questions, pop them out on the Q&A, and I think we're pretty much through the discussion. Yeah.
I think so. Yes.
Excellent. Excellent. All right. Well, nothing's popped up on the Q&A. So, Duane and Nathaniel, I want to thank you for joining the Los Angeles section of the AES and sharing your time with us and your expertise and your knowledge and your passion. We truly appreciate it. And everyone, next month at our meeting, we're going to do a deep dive on Atmos with Nathaniel. And it's going to be a question and answer. So the last ones we've done was the science was the first one, and then the next one we got some folks up and we talked about mixing and this, that, and the other. What we're looking for on this next one is we're looking for questions. So, and it's going to be about questions and answers. And so if you go to the Los Angeles AES website and go to the contact, you can send us questions in advance. And so just send us all the questions you have, and we'll use that as part of the presentation. And then we'll kind of obviously map the presentation a little bit. Nathaniel, did you have something to add? Nope. Okay. And oh, you're muted.
I was just answering a question that came up in the Q&A.
Oh, okay. And yeah, and then we'll also answer questions in the Q&A. But everyone, just send us questions before, and on the Atmos one next month in May, it's the last day of May, May 31st, Tuesday after the Memorial Day weekend. We will do a deep dive on Atmos and answer your most mysterious questions. So with that, everyone who's joined us tonight, I want to thank you very much for sharing your time with us. It was a interesting conversation, and I think we all learned a little bit about it. And with that note, I wish everyone a good night. Stay safe, stay well, and we will see you next month. Peace out, everybody.
Bye all.
All right. Thank you, Duane.
Thank you.
Nate.
Thanks,
All
Duane.
right. Cheers. I'm ending the session. Bye-bye.
Okay.